So welcome to, I guess it's day five. All right, and for those of you in Japan, hope you had a nice, Labor Thanksgiving with no relation to any other type of Thanksgiving. Anyway, so one of the original motivations, as I mentioned back in, I think, day one, was, for a given equation, you want to understand sort of where it fits in a hierarchy. So for instance, the usual Painlevé-6 equation, we understand where that fits in a hierarchy because of Sakai's work. So basically we can both generalize and specialize and have, and moreover have a canonical way of distinguishing sort of what it means to be different types of equation. So in particular, one of the things that pops up is that we realize that Painlevé's original Painlevé-3 equation, if you're familiar with Sakai's work, actually splits into three different equations corresponding to basically, I think it's D5, it's D6, D7, and D8 as root systems. So there's a sort of canonical combinatorics in the picture that lets us distinguish things. And we'd like to be able to do something similar for lax pairs for Painlevé. And we'd also like to be able to do it for higher genus cases or higher dimensional cases like, the simplest Garnier case or the simplest matrix Painlevé case or what have you. And so we want to understand how to do that sort of classification. And there's, so part of the question becomes, we're going to be separating cases based on what their singularities look like. So the question becomes, the first basic question is, given a family of surfaces, which is basically just, we specify how many times we blew up P1 cross P1 or F1 or whatever Hertzsprung surface we started with. So we've blown up m times, or in other words, the self-intersection of the canonical class is 8 minus m. So we can also distinguish the level of blow up by the self-intersection of the canonical class. And a class in PIC. And remember, we have this, from last time, we have this canonical basis of PIC. And so when I specify a class in PIC, I'm really specifying an element in that canonical lattice. And we call that D, with the property that the intersection number of D with the canonical class is 0. So it's actually possible numerically for a line bundle, for a divisor of class D to be disjoint from the anticanonical curve. So what we want to understand is, what are the different types of equation with singularity structure or with singularity information that can arise from a sheaf with Chern class D, so, or equivalently a one-dimensional sheaf supported on sort of a curve of class D. And let's say fixed Euler characteristic. And since we want to allow matrix equations as a degeneration, we should allow the Euler characteristic to be, well, 0 is the simplest way of thinking about it, but actually it's really, they're equal to the order of the equation, but I'll just say 0 to make life a little bit easier. So Euler characteristic 0, say, on such a surface. So this is the basic question that we want to try to address. And the beauty of going to the blow up picture is it actually gives us a natural way of splitting the family of surfaces into pieces, each of which has a different looking collection of of indecomposable, or sorry, irreducible singularities that arise. And then D basically going to tell us for each irreducible singularity, how many times do we use it? Okay, so let's back up a little bit. So given a sheaf on a ruled surface, what does it look like locally? So this is actually a relatively straightforward thing to think about because, well, let me just assume that our ruled surface is F2, because after all, when we're canonically embedding equations, they're on F2. So on F2, what does it look like locally? Well, the point is, our sheaf is, a typical sheaf looks like a line bundle on a curve. And moreover, if it's not a line bundle on a curve, then, well, the support is going to have a bunch of branches. And if we split it up into branches, we can reduce to the case where it's an irreducible curve. And if we have the sheaf might still be a vector bundle on that curve, but if it is, we can write any vector bundle as an extension of line bundles. And so at the very least, there's a filtration. So it's not canonical, but we have a filtration by line bundles on curves. But more than that, we should really be thinking about, if we want to understand what it looks like locally, we've really said we're fixing a fiber, and we're asking what's going on in a formal neighborhood of that fiber, basically. And so in the formal neighborhood of the fiber, we may be able to further break things up into branches. And again, so what we really have is locally, we reduce to the case of a single branch. Okay, and we have the following standard fact. Which is that any irreducible polynomial over, well, let me just be really lazy and work over C. So any irreducible polynomial, so we can think of this either as a standard algebraic geometry fact or a standard fact about holomorphic functions, which I teach in my graduate complex analysis course every year, so it's very standard. Any irreducible polynomial over C double bracket X admits a parameterization of a root where basically X is some power of n, some power of u. And in fact, if this is of degree n, that's the n. And then y is some rational function in general of u. Okay. And so in particular, what this is telling us is that any irreducible curve in P1 over the power series ring is rational. In particular, it has a rational parameter. Well, let's say formally rational. That it has a parameterization. Okay, so in other words, we have this thing where basically y is some Puiseux series in X. And here I'm assuming, since we remember we have 3 homogeneous coordinates where y has degree 2, and I'm assuming that we're in a patch where w can be taken to be 1. And of course, if we have a general parameterization of a map from spec of k double brackets u to f2, either w is a unit, in which case we can divide by it, or it's not a unit, in which case x is going to be forced to be a unit and we can divide by it. So either way, we can sort of make everything work reasonably well. So we have this situation, but this can be turned into at least a formal equation. So as an example, if our anticanonical curve is y times y minus xw equals 0, which remember is going to look like this. This is the case corresponding to Q difference equations. And suppose we're given a parameterization of the form. Oh, sorry. Here, this might be x minus a to the 1 over n in general. Okay, but let's suppose in this case that it really is x to the 1 over n. So this is our sort of formal spectral curve. Then what does this translate to in terms of b naught and b infinity? In terms of our actual equation. Well, if we ignore the fact that we took this n first, then this is very straightforward. We basically have b infinity is y, and b0 is, or y restricted to our curve, and b0 is y minus x on our curve. And so we see that b infinity is f of, f of x to the 1 over n, and b0 is f of x to the 1 over n minus x. So our equation is v of qx equals b0 over b infinity. So 1 minus x over f of x to the 1 over n. So the upshot is that, and we can do this for any of these other possible sort of natural choices of the anticanonical curve. So the upshot is that if you hand me a parameterization of a branch, you can turn that into, a local description of an equation. And of course, we always have to deal with the fact that, yeah, okay, we're kind of cheating here. It really is Q is really 1 here. So, this is not quite an equation, but it would be the appropriate Higgs relaxation. But one of the general principles that always applies here is if you pretend at appropriate places that you really are working with equations, things end up actually working the way you expect. So this really does sort of give you the right thing as far as equations go. Okay, so this is the general way we can proceed here. And we can do this for each of the different types of equations. It's a little bit trickier in the symmetric cases because there you have to basically take into account a choice of parameterization of the actual anticanonical curve, because that's where the equation really lies. but that's easy enough to parameterize in the two cases that aren't just elliptic. And in the elliptic case, there's just not that much interesting going on with singularities. So there's not too much to say there. Okay, so this is how we can sort of make this work. And we can, of course, go backwards. So given such a formal equation, we get, by the usual sort of just factor it in the usual way, but now it's factoring into 1-by-1 matrices. So that's really easy to take into account cancellation and everything. So we set it, we get a corresponding parameterized curve in F2. Now, originally, of course, we got a line bundle on a curve, but since we're local, we don't see the difference between the different possible line bundles. We just get a curve in the end. So local behavior of the equation gives rise to local information about the spectral curve. So far we're saying something. Now, what we can then do, if you like, is we could take this local information and then start blowing things up. And so basically, given the local parameterized curve, you can tell whether it meets the anticanonical curve. And then you can blow up the appropriate point of the anticanonical curve if it does. And then that gives you you can lift the parameterization to the appropriate patch and then keep blowing up. So approach 1 to getting our surface XM is explicitly blow things up. Now, there's a couple of issues there. The first is that you actually have to start with the chosen singularity. And so it's not so helpful because we'd like to be able to go in reverse. Because at the end, we're going to want to be able to say, okay, these are the different types of things. And then for each one of those, we can say what the different singularities are. I mean, what the different singularities look like. And so having to start with a singularity and then start blowing things up is a little less satisfying. But the other big issue is that it's not clear how much precision we need. I mean, after all, we're taking this parameterization over the ring of formal power series. That's something you can only work approximately in. It's a non-Archimedean local field. You can only do things approximately. I mean, it's better because you don't have round-off error or anything than working over C itself, but it's still kind of annoying. You can only ever do approximations, and so you're sort of stuck between either you calculated too far out, in which case you've wasted effort, or you didn't calculate it far, you don't calculate it far enough out, in which case you don't actually know what surface you end up with. So this has been an issue. But the other is just that, typically the way you're going to do this, if you're actually going to be doing this approach, what you're actually going to be doing is not looking at local singularities. You're going to be starting with one particular equation and doing the blowups to separate it from the anticanonical curve to give you one particular surface. So we need to be able to say a little bit better. So, but what we can say is the following. Given a particular surface XM, we can again split the spectral curve in a formal neighborhood of the pre-image of a fiber. And what we're going to find is that each branch is going to meet some component of that fiber. Just because, well, I mean, either we have vertical components, in which case we can remove the vertical components without affecting the equation. And we should do that because that's basically telling us we have an apparent singularity. Or it's purely horizontal. And so each branch is going to be meeting the fiber at a distinct point. And each of those components where it meets the fiber is not going to be in Q because we're assuming that we've separated ourselves from the anticanonical curve. Okay, now what we can then do is we can look for well, if the fiber has a -1 curve, that is, if it contains a -1 curve, not meeting any branch, or let's just say meeting the chosen branch, we can blow it down without affecting anything. Because basically we've split our curve up. So we split our equation up into these irreducible pieces. And then what we're really doing is we're basically saying we're just blow up the irreducible piece until it's separated from the anticanonical curve. So if there's a -1 curve that doesn't meet the chosen branch, we might as well blow it down. And we then keep doing that until all we're left with is, only the components that actually are needed to see our branch, to get the chosen branch. Okay, moreover, when we do this, what we're going to find is that our branch our chosen branch is necessarily going to meet a -1 curve. Because if it doesn't, that had to have arisen somehow. Well, sorry, or or the branch is non-singular at that point. In which case, well, we don't really care about that case. We know what non-singular equations look like locally. The point is, because it's non-singular, because it's singular at the point, it did meet the anticanonical curve, which means once we blew up a point to start separating it, it was now meeting a -1 curve. And each time we blow up a point to blow up a next point to separate it further, it's still going to be meeting a -1 curve. So since we were being parsimonious and we're only blowing up the absolute necessary, it's finally going to stop when the -1 curve it meets is not contained in the anticanonical curve. Okay, so far so good. Given, well, so we can describe the local parameterizations meeting that -1 curve and not meeting Q, and we can basically just, and we can do it in basically using big O notation in the appropriate patch. Of the blowup. So the point is, if we draw a picture, our patch looks like an affine space, because after all, everything we're doing is starting on something rational, and then we're starting to blow things up. And we have one, sorry, right, the red is not visible, is it? We have, inside here, we have one curve, which is Q. And then we have our spectral curve. Sorry, we have our -1 curve, E. And then our spectral curve is meeting E, but not meeting Q. Okay, but we only care about what happens in a formal neighborhood of E. And so if we think of our coordinates as, usual X and Y, so E is basically X = 0, and Q is basically Y = 0. We can do this because the only cases we're going to be doing any sort of serious blowups is when Q is going to start picking up multiple components, and all of those components are rational. So eventually Q is basically, we can take the parameterization of Q as one of our coordinates, essentially, or parameterization of the visible component of Q will be one of our coordinates. And so we see that our curve is basically Y equals f of X, where F is a unit. Or in other words, Y is, let's say, theta of 1. So that is, it's some non-zero thing plus lower order terms in Archimedean land. Okay. And then what we can do is we can take this parameterization and start blowing things down. So this induces a parameterization. On blowing things down. And in particular, if we keep track of this theta of 1, what we're going to find is that eventually we get Y is going to be some approximation, some approximate function of U. X will be some approximate function of U, where U is whatever coordinate we had from on the previous, in our parameterization there. And then W will be some, I guess these could be different approximations. So when we trace everything down, this approximate parameterization upstairs turns into an approximate parameterization on X, on the original rule surface. Okay. Now, the benefit of this approach is this tells us exactly what information we have coming from the fact that our curve, our spectral curve, has been separated from Q by the given sequence of blowups. So, anything we change, I mean, in principle, to actually have a parameterization of the spectral curve, we need to fill in, all of these higher order terms, or lower order terms, really. But anything we do there is just going to change this curve by, moving it somewhere else that's still basically being separated by the same sequence of blowups. So this is telling us exactly what information we have encoded in the fact that this sequence of blowups separates us. Okay. And then what we can do is, so if well, suppose this has x equals 0, w equals 1 at our base point u equals 0, corresponding to the actual point where our spectral curve meets this last exceptional curve. Then we can rescale to make w actually equal to 1. And of course, I should say, we're getting down to, every time before we end up on F2, we're working on an affine patch. So, this is just a question of choosing the correct affine patch to get started on. Okay. And then what we're going to see is that y is going to be, some multiple of some power of u, and x will be some multiple of some power of u. And we can solve for u. And this is just the standard thing in complex analysis, namely, you take this right-hand side, you take the nth root, you invert that power series as a, take the inverse of that power series under composition. And that gives you u as a power series in x to the 1 over n, and then you plug that into y. And so this gives us an expression for y as a Poisson series in x, which is what we wanted. But we get it. Oops. Up to some specific and explicit error term. And so in the end, if you follow this down, undo all the blowdowns, undo all the blowups, you eventually get a parameterization of y where you're told exactly what information got encoded upstairs, okay, by the fact that this sequence of blowups separates you. And I should say, this, of course, I didn't really say earlier, but this gives you an equation involving x to the 1 over n, but you really get n different equations because there are n different nth roots. And if you then take those n equations, take their direct sum to give you a big diagonal matrix, and then conjugate by the right thing to basically get rid of you can get rid of the appearances of x to the 1 over n, and you get an nth order equation such that the spectral curve factors as those n branches. So that's sort of the very last step in doing this interpretation. Okay. And better yet, we can do this procedure in a qualitative way. That is, if we're only told sort of the gross information about our blowups, namely which components of Q contain each point being blown up, this tells us which coefficients can appear in this function f. So in particular, there's sort of there's a couple of different things that can happen when you blow up a point. If it's on more than one component, then that point is uniquely determined, and so you don't get any degrees of freedom. And but also you get a new component of the anticanonical curve. And this also, of course, happens if it's a singular point, because well, except in the non-reduced case. But basically, if it's a singular point of the reduced anticanonical curve, then again, you spawn a new component, but you don't get any new parameters. If it's on only one component, then you get a parameter, which is typically going to either be an element of the multiplicative group if that component meets two other components, or an element of the additive group if it only meets one other component. And so in particular, what we actually get is not just which components can appear, we also get told which components must appear, which are basically the ones where the parameter is an element of the multiplicative group. So for instance, what you get if in the case of a differential equation is, well, so there's actually a known classification of local singularities for differential equations, which again gives you this Puiseux series type factorization. And so the existing classification gives v prime equals well, let's say near x equals 0 gives you v prime equals f of x to the minus 1 over n plus big O 1 over x, where times v, where we actually call this p, where p is a polynomial. Okay. And here we should put a x to the minus 1. And really, we should take p mod constants. Oh, sorry, that's not right. This should be little o. Okay. So, this is what the classification for differential equations that you'll find in the literature of irreducible singularities looks like. Okay. However, in our case, so the classification coming from surfaces, we get a refinement. So in particular, what we're told, so here, in the existing classification, basically the only information that's sort of the only gross information you get is n, i.e. what root are you taking, and the degree of p. So you're basically just told, what's the, well, apart from what the denominator is, you're told what the leading coefficient is. So what we actually, in the case, if you actually do this for using the surface perspective, what you get is that the combinatorial data actually specifies well, firstly, the highest degree term with the denominator, well, just let's say the highest degree term but also every term where the denominator of the exponent jumps. So in particular, a typical sort of thing might be, something times x to the minus 3 plus beta times x to the minus 2 plus gamma times x to the minus a half, sorry, x to the minus 3 halves, plus delta x to the minus 1 plus little o of x to the minus 1. And this is a different type of singularity from the case where you also have a, say, x to the minus 5 halves term in there. In particular, the number of blowups you have to do to separate this singularity, to separate this equation from the anticanonical curve is smaller, and its contribution to the expected dimension of the moduli space is also smaller. Okay, and in particular, when we do this procedure of, taking whatever surface we end up with and saying, okay, which things are forced to be non-zero, which things are allowed to be zero, we see that alpha and gamma are forced to be non-zero, because if you make them zero, you are changing the type of singularity. But these other coefficients are allowed to be equal to zero, and will not change the surface if you do that. Okay, and you can do similar things. The additive case is similar, except now we have to be at x equals 0. Sorry, well, let's say z equals 0. So sorry, around z equals infinity. And there's also this slightly annoying thing. There can be an overall power of z. But basically, you're left with a very similar thing where, again, it's just basically you're specifying, in this case, instead of the logarithmic derivative, you're specifying the logarithmic difference. And again, basically, the important information is where the jumps in the denominators happen. And of course, part of this, of course, is, if I tell you where the jumps in the denominators happen, well, okay, you can also take the LCM. Sorry, when I say jump in the denominator, I mean the jump in the LCM of the denominators. But in any case, so we see there's a jump here and there's a jump here. So n is 2, so far and so forth. Okay. Now, what does this look like in terms of the surface? Well, in terms of XM, this combinatorial data namely, whenever we blow up a point, which components does it lie on? Well, this is telling us exactly how Q splits into components. And moreover, it tells us, what those components are in our universal Picard lattice. So, for instance, on x0, Q is, well, I'm assuming we're in the even case. Q is 2s plus 2f in the simplest version. This is going to be a symmetric difference equation if it's irreducible. And okay, if we blow up a point, it can be a generic point, in which case we're just going to get a finite singularity, and there's not too much we can do past that point. So the other possibility is that we're going to blow up the singular point. So if we blow up the singular point, well, what's going to happen is we're going to pick up an extra component. And so Q is going to now have, the exceptional curve is going to be one of the two components. And then what's left over has this class 2s plus 2f minus 2e1. Okay. And if you look at this picture, you see that there's two possibilities, depending on whether the curve is multiplicative or additive. So it either looks like, the usual thing where we have two components meeting at two distinct points, or it's two components that are tangent. Sorry, it's very hard to draw two tangent things, but pretend that's a tangency. Okay. So if the next point we blow up, again, it could just be a generic point of the exceptional curve, in which case, we get either, in this case, we get a non-zero parameter. In this case, we get a non-zero parameter. In this case, we get a parameter which is not infinity, say. But if we blow up a point of intersection, so in the multiplicative case, we have to decide which of these 2 points of intersection they are, which is basically 0 or infinity. This is hard to distinguish geometrically because there's this overall symmetry that we can just invert everything. So there's one thing that sometimes you may want to do a slightly more refined classification where you do distinguish between 0 and infinity. In any case, if it's a point of intersection, then, well, it has multiplicity 1 on the main component, multiplicity 1 on the new component, and the total multiplicity is still 2. So we pick up one copy of the exceptional curve. And so now this is our picture. And again, there are two possibilities. It can look like a triangle, or it can look like 3 lines meeting at a point. And then, we keep going, and you say, okay, well, let's suppose it was 3 lines meeting at a point. Then, we have to remove that component from each of these original. You have to remove the new exceptional curve from each of the original components, but we're only allowed to remove an overall once, so we're left with 2 copies, and so now we get this double copy of E3, and we can keep going. So and the key, one thing to note, which is nice, is that it turns out you can show without too much trouble that the only case where you could be on 3 components is when you have 3 multiplicity 1 components meeting at a single point. And this is, if you're familiar with elliptic surfaces, this is exactly corresponding to the fact that there's only one case on an elliptic surface where the special fiber has a triple point that's coming from 3 reduced fibers. Everything else is just basically 2 components, which may have high multiplicity, but it's always just 2 components meeting. Okay, and this fact is what makes it possible to do this overall thing of figuring out the qualitative information about the parameterization, because that means that after a small number of blowups, you're left in a situation where you're on an affine patch where Q has 2 components with some multiplicities, and then you're blowing up the origin. And so then it's relatively straightforward to figure out how the parameterization carries through, especially since if you're willing to occasionally do this trick of reparameterizing to basically solve for one of the 2 coordinates. And that's how this procedure works to really keep track of things. Because otherwise you have sort of two parameterization. It's hard to keep track of your degrees of freedom if you keep going too far. But if you reparameterize every once in a while and use some lemmas about how that doesn't do too many weird things, you can trace everything through. Okay, so the idea is the different types of singularities correspond to different decompositions of Q plus, in very high level cases, whether Q is smooth, nodal, or cuspidal. I mean, basically, if you only have one component of Q, then you don't know a priori whether it's smooth, nodal, or cuspidal. And if you have two components, you can't tell whether those two components meet in two distinct points or whether they meet twice in a single point. And if you have three components, again, you can't tell whether it's a triangle or a star. After that point, it's either going to be a polygon, so nodal, or it's going to have a multiple component, which is basically the cuspidal case. So cuspidal includes non-reduced. Okay, so in particular, basically this pure combinatorial information of, how does Q break up into different, we want to write Q as a union of components or as a sum of linear combination of components with positive integer coefficients. So what are the classes of those components in this canonical basis of the Neuron-Savary lattice? And what are the actual coefficients? What are the multiplicities? And that's the combinatorial information. And then if you happen to have three components or fewer, and they're all multiplicity 1, then you have this slight extra data of, is Q smooth, nodal, or cuspidal? So basically this really does turn it into a combinatorial question. So given our original problem, we're given D in pick of XM. We just need to classify the different ways that Q can decompose. Okay, and there's a straightforward approach. Which is almost certainly not the best way to do this, but I'm not actually sure what the best way to do this is. And this at least is easy to program and works in small cases. I mean, at some point you start getting into combinatorial explosion issues and you run out of memory or what have you, but it works for reasonably small cases. Which is basically we start on X naught. And the point is on X naught, we know what the possible decompositions are. So for instance, it's, again, assuming we're in the even case, Q can be 2s plus 2f. So i.e. Q could be irreducible on our starting ruled surface. It could be s plus f plus s plus f, i.e. two components. It could be s plus f plus s plus f. It could be s plus f plus s plus f. And there's not too many things. Eventually you get into the cases where it's twice s, that it is non-reduced, plus f plus f, or twice s plus 2f. Now, eventually you can do even worse things. For instance, it could be 2s minus 3f plus some partition of 6. So let's say 4f plus f plus f. Now, okay, so we have a slight problem here. There's infinitely many possibilities, but there's not too many overall types of possibilities. I mean, basically, we're just left with either we're on P1 cross P1, and there's just really not that many things we can do. And there's, I think, 16 things we can do on P1 cross P1, or we're on some degenerate surface, some degenerate Hertzsprung surface, in which case, S is not irreducible. So our irreducible components is going to be S minus F or S minus DF or some larger value of D. And then you can basically say without too much difficulty that, okay, it's either going to be, S minus DF plus S plus DF plus F plus F, or S minus DF plus S plus DF plus 2F, S minus DF plus S plus D plus 1F plus F, or S minus DF plus S plus D plus 2F, or twice S minus DF plus some partition of 2D, or of 2D plus 2 times F. So basically you have some number of different fibers occurring with different multiplicities, the total of which has to be 2D plus 2. And so for any given D, you can write down all the possibilities very easily. And we'll ignore the fact that for D large, this is growing like e to the square root of D, the number of possibilities, because in practice, D will never get large. Okay. So the point is, for D greater than or much bigger than 0, that component, S minus DF, which is forced to be in the anticanonical curve because it has self-intersection smaller than -2, has negative intersection with our chosen divisor class. But that means we can't get that surface. So just by looking at which D's can occur here, if we look at the biggest D such that this is non-negative, that cuts us down to a finite number of initial possibilities. Okay, and of course we can do something similar if we wanted to start with an odd Hertzsprung surface. And in general, a priori there's no difference between whether you start even or odd. You're going to get the same set of possibilities. Some ways of structuring the calculation, it may be more straightforward to do it starting with odd or starting with even. Okay. So we can enumerate the possibilities on X naught. So to get the possibilities, as you get the enumeration on X1, we just loop over all possible choices of which components contain X1, i.e. the point being blown up. So the point is, we have this decomposition of X naught. Among other things, what this tells us is the intersection numbers between the different components. And because we've broken Q into irreducible components, all of those intersection numbers are going to be non-negative. So in particular, Well, so one possibility is x1 is on only one component. Okay, well, it's clear how to enumerate those possibilities. We have one such possibility for each component. The next is it's on 2. And those 2 components must have positive intersection, because if we are blowing up a point that's on both components, they'd better intersect at least one point. So, so the next thing we do is we loop over pairs of components that have positive intersection. And then the third possibility is that it's on 3. And Q actually splits up as 3 components, any 2 of which meet in a single point. There are actually, in general, of course, going to be several different ways that arises, but we get that. So this gives us the possible points we're blowing up. And it's worth noting, in case A, the number of parameters goes up by 1. In the other cases, the number of parameters doesn't go up by 1. So modulo figuring out, how to compute the dimension for the different possibilities in X0. Once you've done that, this inductive procedure carries through and lets you compute the dimension on each further blow up. Okay. Moreover, the new Q in case A, we take the component that contains X1 and we subtract EI. Well, I should say, of course, in B, we also need to take into account the possibility that Q might be irreducible and we're blowing up the singular point. So basically, if we're blowing up one point, if it's just on one component, then we get QI goes to, we just subtract EI from QI because it's a smooth point of that component, in general. And if the multiplicity of QI is bigger than 1, we get a new component, EI, well, EM, with multiplicity MI minus 1. Okay. In case B, well, okay, you can adapt the singular case correspondingly, but basically QI and QJ get subtracted. And we pick up EM with multiplicity MI plus MJ minus 1. In case C, well, this is the star case. So we get Q1 minus E, Q2 minus E, Q3 minus E, and E with multiplicity 2. So it's very straightforward to figure out the new decomposition of Q after the blow up. Here, let me just get rid of the subscript. It's whatever subscript it is, of course. Okay. So, but the other thing we can do is some of these will have components having negative intersection with our chosen divisor class, so they get thrown away. Okay, now, okay. In pretty much any case, this is going to give you an enormous set of possibilities. But it will at least be an exhaustive set of possibilities. Okay. To cut this, the other thing to note is that this is giving us stuff for general surfaces X. So this is only going to give us equations up to scalar gauge, because this blowdown structure we have is not ending with F2. So we don't have a canonical translation to an equation. We only have it up to scalar gauge. So since this only gives us equations up to scalar gauge, we should then mod out by the action of dm. So remember, this is reflections by ei minus ei plus 1 and f minus e1 minus e2, none of which change the ruling. And so therefore, none of which actually change what the equation is up to scalar gauge. All they're doing is basically changing the bookkeeping of how we eventually get down to P1. Okay, so, and this gives us a much, much smaller class. And there's some technical things which haven't had to deal with in the actual calculations I've done, which would get somewhat more annoying. For instance, the fact that dm is only in general a groupoid means that modding out by the action is in general going to be relatively complicated. For the cases of interest, it turns out you can enlarge it to a somewhat bigger groupoid by saying, okay, well, if I have this component, if one of my simple roots is already a component, then I just take the reflection in that root to do nothing to my decomposition, rather than sort of negating that root. And it turns out that actually still gives you a well-behaved groupoid. And so as long as you don't pick up really bad -3 curves or worse in this process, you can mod out by the groupoid as an actual group action on your set of possibilities. And so you can use existing magma support for how you figure out orbits of group action. It's not too bad. But in general, you might actually have to do the full groupoid thing, and it would be a bit more annoying. Okay. And so what this gives you, this gives the classification of possible lax pairs for an equation, for an isomonodermy equation of given type, or the classification of rigid equations of a given type, if instead you started with D corresponding to a -2 curve. Now, for the first thing, you might as well take D to be in the fundamental chamber. Although, it's worth noting that if you actually want it, I mean, you can take it to be in the fundamental chamber, and that'll give you, a lax pair for every possible isomonodermy equation in your family. On the other hand, if you want to allow slightly more complicated lax pairs, you could allow something not in the fundamental chamber for that. For rigid equations, you really want to allow things not in the fundamental chamber because, well, for one thing, roots are actually never in the fundamental chamber. But also, we mentioned last time that when you reduce a root, it's going to end up being S minus F. It'll just be the trivial equation. That's not very interesting. You really want to end up with something non-trivial, which of course is not something that, which is always going to have some possibility of being reduced. So, and let me, as an example, the 2f1 equation. Well, what does 2f1 look like? Well, okay, there's a little bit of choice, but one way of writing it is it's a double component, which actually is the -2 curve on F2. This is not the standard embedding in an F2. This is something that's only up to scalar gauge. And then it has 4 singular points, which are 4 components, each one of which we're then blowing up a point on. Yeah, no, that's not right. We have, it's 2f1. We have 3. and we have, so we have 3 singular points, 2 exponents for each. So we need to blow out, so that gives us 2 branches because we have 2 irreducible singularities. We need to blow them up both twice. So this is what the decomposition of Q looks like for the standard Gauss hypergeometric equation. So D is 2s plus f minus E1 minus E2 minus E3 minus E4 minus E5 minus E6. And you can check that indeed this has self-intersection -2 and is disjoint from Q. And moreover, for this particular decomposition of Q, it's orthogonal from each of these pieces. A big thing to note here is that because we've excluded the possibility of it having negative intersection with everything, you'll be forced to basically, you can't blow up a point of it on a component that has intersection 0 with D. And so you're always decreasing the intersection with D every time you blow of some component when you blow stuff up. And so eventually you're going to end up with, every component being orthogonal to D, as it should be. Okay. And so the corresponding classification of surfaces gives you hypergeometric equations. All right. And so now I look up the answer. What'd you get? Well, so what do we get as our classification? Well, there's a fair number of possibilities, but we find that there's one elliptic equation, which of course there's always going to be an elliptic equation. Of course, there's always going to be symmetrical elliptic because we're in the rational case. So in particular, one thing we automatically get from this, so we start with a 2f1 equation, turn it into a sheaf, look at what we did to the anticanonical curve, look at what that tells us about the Chern class, is that immediately tells us sort of what the elliptic equation in the hierarchy looks like. It's a second order equation with 6 singular points. And indeed, there's a notion of elliptic hypergeometric function, and it satisfies an equation of second order with 6 singular points. Okay, there are 10 symmetric Q difference equations. There are 8 symmetric difference equations, ordinary difference equations. There are, I have to do everything in my head, 23 non-symmetric difference equations. Sorry, Q difference. 9 non-symmetric difference, and 5 differential. And of course, the differentials include very familiar things like Bessel functions and stuff like that. Okay, now there's a couple of things to say here. So the first is, this tells you the different possibilities modulo this question, this notion of what it means to be, what the different kinds of singularities are coming from surfaces. But there's some hard problems. The first is, which of these, I want to say 41, but you should do the addition yourself. Which of these 41 classes degenerate to which others? That is, for which, if I start with an equation of one class, it has so each class has a certain number of parameters. If I start with an equation of that class, and then take a limit as the parameters vary, I will in general be able to get other classes arising as limits. Which classes can I get? And also, can I get everything of that class, or is there some subclass which is the only thing I get? So this turns into a geometric question. So each piece, i.e. each way Q decomposes plus smooth or hospital, plus this minor detail in the cases where it doesn't decompose very much, has a closure in the moduli space. I'm putting scare quotes because it's actually a stack, which I will try not to have you actually need to know what a stack is. But it's more complicated than just a scheme or even algebraic space, but it's a perfectly reasonable algebraic object and a familiar type of object for people who deal with moduli problems. So it has a closure in the sort of family of all surfaces, or of all anticanonical surfaces. So the first question is each such closure a union of pieces? So basically, we've taken this family of all surfaces. We've thrown out the surfaces where D has negative intersection with some component of Q. That gives us something which is actually a finite, still a stack, but it's a finite type stack, much better behaved. And inside there, we have the closure of each of our pieces. So in particular, the elliptic piece, the closure is going to be everything. Okay, that's clearly a union of pieces. But if we look at some lower piece, one particular symmetric Q difference equation, its Zariski closure in the family of all surfaces is some subscheme or some substack really. And we want to know, is it a union of pieces? And if so, which pieces? And if not, we actually want to refine things to make it work. Basically, if you have a closure of a piece which is not a union of pieces, that means it's meeting some piece in a closed subset of that piece. In fact, each piece you can really think of as a scheme. So it's meeting that piece in a closed subscheme. And so you should really be thinking of those that subfamily as a different type of equation, because those types of equations can be obtained as limits, whereas there's the slightly more general things in what we thought was the right piece can't be. And so we can actually separate that by a geometric characterization from the general pieces. So the fancy way of saying this is that we've broken ourselves up as a disjoint union of pieces. We want to know, is it a stratification? Because basically a stratification is such a decomposition such that every closure is a union of pieces. And moreover, we want to know what poset we get. That is, which pieces appear inside which other pieces. Okay, so that's already a hard problem, it turns out. And when I say it's a hard problem, what I mean is, to give you an idea of how hard this is, one version of this question is, in the family of, let's say, elliptic surfaces, with a chosen anticanonical fiber, which is basically the classification for Pan-Lavie lax pairs, or just Pan-Lavie equations. We can ask, okay, what are the different possibilities for how the anticanonical curve splits up? And there are 22 cases, and this is Sakai's hierarchy. I was at a conference a number of years ago where several people put up a slide that had, this is the diagram of which pieces degenerate to which other pieces of these 22 types. And I think there were like 3 people who, I saw this diagram in 3 different places. Each time it was different and none of them were correct. So this is really a quite subtle problem. And so eventually, I actually have code, if you're interested, that basically takes 10 seconds in Magma that actually explicitly computes for each one of these 22 cases the equations that have to be satisfied by the coefficients of the elliptic surface in order for it to have that type, and then just precisely checks for each of those closed subschemes, which ones contain which others, and verifies that it really is a stratification and tells you what the poset is. But it really is quite subtle. The other reason it's quite subtle is that A is actually known to fail if we work over Z. So in particular, in this elliptic surface case, in this Pan-Lavie case, so one of the things that happens is, for instance, there's this A8 case where so A8, which is basically Q is a nonagon. There's E8, where Q is horrible. And naively, if you look at things, I mean, there's a relatively easy sufficient necessary condition that's satisfied here and makes you think that A8 might degenerate to E8. And what you find is that A8 does not degenerate to A8 over C, but over F3 bar degenerates to a subfamily. And moreover, once you start working over once you're not just working over C and you're working over Z, you should also allow yourself to degenerate from a p-adic case to FP. And so in particular, you can also degenerate from Z3 down to F3, and there it degenerates to the E8 case. So A8 is basically the most degenerate Q Pan-Lavie type thing. In fact, it's so degenerate, it's not really an equation anymore. E8 is Pan-Lavie 1. But basically, what you find is that if you work over Z, characteristic 3 Pan-Lavie 1 turns out to be a degeneration of A8. Whereas over C, it's not. So in particular, this fails to be a stratification because the E8 piece has this sub piece, which is the characteristic 3 fiber that behaves differently relative to limits. Okay, so that's one reason why I don't actually know the answer to this question, is because I actually know that if you work over Z, it fails. So that means you have to use some information coming from the fact that you're in characteristic 0 if it's going to hold in characteristic 0. And it's not clear. I have an additional necessary condition, which I'm not actually sure is computable, although I can check it in enough cases to prove that A8 does not degenerate to E8 without using this brute force actually computing the ideals classification. But it's a bit of an issue. There's another hard problem. Which is that if an equation of type 1 degenerates to an equation of type 2, we should be able to write the equation, a typical equation of type 2, as a limit of equations of type 1. This turns out to also be subtle, because the geometry tells you that there's a limit relation. It doesn't tell you anything about how to get the limit. Now, probably if one were really careful, you could get this work. But it's because problem 1 is already hard. That means it's not necessarily that easy to write down the surface of type 2 as a limit of surface of type 1. And if you can't even do that easily, certainly getting the equation limit is going to be hard. And then hard problem 3. Given a limit of equations, prove a limit for solutions, or at least one solution. So as an example, there's a Q area equation in the 2F1 hierarchy, which is basically the most degenerate non-symmetric Q difference case. And the geometry tells us it degenerates to the area equation. It turns out this limit is we're talking about a Q difference equation and a very simple Q difference equation. It turns out that to make the limit work, you have to take a scaled limit around a quarter, x equals a quarter, which is a completely random looking point relative to this picture. And you can then check that that scaled limit of the equation is the area equation. It's still an open problem to show that the Q area function degenerates to the area function, despite the fact that the way I figured out that I was supposed to take a scaled limit around a quarter was by looking at the Q area function for Q really close to 1, looking where the zeros were and saying, hey, those look like the zeros of the area function once I rescale properly. So it clearly is the case that the area function is a limit of the Q area function, but it's still an open problem. Now, of course, hard problem 2 is purely algebraic. Hard problem 3 is analytical. So, we expect it to be harder, at least for an algebraist. But anyway, so there's definitely some big open questions here. So in the 2F1 hierarchy, you can actually solve this poset problem without too much difficulty. So hard problem 1, you can actually solve. And similarly for the Pain-Levé case. But in general, it gets tricky. Okay, for Pain-Levé, we have something like 61 different lax pairs, different types of lax pairs, split among the 22 different equations. For Garnier, well, simple for genus 2, i.e. dimension 4, we get the matrix Painlevé cases, which are, I think, 62 lax pairs. It's essentially the same classification as Painlevé, except there's like one extra case that splits off. And then there's the Garnier cases, where I've forgotten the number, but it's pretty big as well. Okay. Now, it's worth noting, these are all, for the Garnier case, these are all second order lax pairs. It turns out for higher order Garnier, the lax pair is unique. You know, there's the minimal lax pair is uniquely determined, and it's always second order. But for instance, there's a classification of genus 4, of continuous genus 4 isomonotony problems. And there, you end up getting a number of higher order things that are all differential equations. But in each case, you note if you do this process of turning into a sheaf on a surface, it's not in the fundamental chamber, unless it's a matrix Painlevé case. It won't be in the fundamental chamber. You can then do the sequence of integral transforms to put it into the fundamental chamber, and it'll be one of these Garnier cases. And then, of course, you also get discrete Garnier as well. Some other things you see is you can predict the number of continuous deformations as basically it's the actual dimension so the actual number of parameters minus the number you would guess based on the number of components. I.e., the dimension of the top additive case, or the top symmetric difference case, plus 1 minus number of components. What this has to do with is the isomonotony transformations. The discrete isomonotony transformations are twists by line bundles, and so the number of twists by line bundles is the, I mean, of course, it starts out as just being pick of x. So there's m plus 2. But if you twist by a component of Q, your disjoint from Q, you're not going to change your sheaf at all. So every component of Q gives you a discrete isomonotony transformation that becomes trivial on that piece of your hierarchy. And so that's basically where this calculation comes from, of you figure out how many discrete deformations you have. And then it turns out the number of continuous deformations is, you have one isomonotony deformation per parameter. And so if you have too few discrete deformations, you pick up extra continuous deformations. And this can actually be checked, although it actually involves looking at the non-commutative theory to make this work. There are also higher order, as I mentioned earlier, minimal lax pairs for the Painlevé case. Where we basically have there's still the same 61 possibilities, but all multiplicities get multiplied by some fixed number R. And as far as I know, these have not actually been worked out explicitly even for R equals 2. Or for any of the cases where R equals 2. I could do it. But so there's a lot of extra things. As I mentioned earlier, this is basically coming from, there's one for each rational number because we can specify the degree of the vector mode as well. Note, for d equals 1, we have a straight line form. And so the d equals 1 case is probably the easiest one to try to work out explicitly. For R equals 2, I mean, the only thing we care about is that d is relatively prime to R. So if R is 2 or 3, you might as well take d equals 1. But in general, it's going to be, oh, sorry, it has to be relative prime to 2R. So if R is 2, 1 and 3 are basically the only possibilities mod R, but you can dualize to turn 3 into 1. So it's really just 1. So you might as well, you only really have the straight line form there. Past that, there are more possibilities, but these are the main cases. So I think this is where I should stop. And then next time, I'm actually going to say some stuff about the non-commutative picture, but I wanted to sort of give you the idea of how one does classifications in this picture, because that's kind of really the big payoff for a lot of the integrable system side is you don't need to know why this works. If you can do this classification that tells you all the different possible lax pairs, and then you can just calculate those the way you would normally calculate lax pairs, even except for the elliptic case, you just basically say, okay, well, I'll just write things down explicitly, parameterize, find some way of parameterizing things, and that gives me my lax pair. And then I just check that that satisfies the right thing. So there's a paper of mine with Ormerod where we do this for the symmetric difference lax pairs for Pan-Lavie equations, for instance, where we just basically say, okay, the general theory tells us that there should be a symmetric difference lax pair for P6 where the singularity looks like this. And then we just say, okay, well, let's look at what an equation with this kind of singularity looks like. See, it's okay, it satisfies certain equations. We figure out a way of rigidifying that so we can parameterize it, and then check and then see that that actually does satisfy a continuous isomonotropy deformation, which is Pan-Lavie 6. So to some extent, you don't actually need the non-commutative theory to do the integrable system stuff. All you need is basically all this commutative theory I've developed. But then the payoff is that if you actually want to prove that everything works, that's where you need the non-commutative theory. And that's what I'll be saying some stuff about next time. Okay. So this is the end of lecture 5. And so the last lecture will be tomorrow. Throw the floor open to questions.
So I was intrigued by the story on degenerations. In particular, I mean, of course, by everything, but that particular point I wanted to ask about. At one point, you said the characteristic 3 case for Pan-Lavie 1 is given by A8.
Well, it's a limit of A8.
It's a limit of A8. Okay. But,
well, basically, in algebraic geometry, we've imposed one more equation, namely 3 equals 0. And so the dimension is 1 lower than the usual E8. I mean, the simplest way you can tell that A8, the general A8 case can't degenerate to the general E8 case is that they have the same number of parameters. So you can't, so you can't possibly get a general degeneration, but you can actually make it have 3 equals 0.
Yeah. What I'm struggling to understand is how to interpret that as a dynamical system.
Yeah.
So in the case of Pan-Lavie 1, I have a different derivative, right?
Yes.
Which drives the flow. How do I understand it in the other?
So remember how A8 has this issue that it behaves kind of badly as a dynamical system because there's a sort of order.
Oh, yes, of course. Yes.
Yeah. Well,
yes.
Differential equations with finite characteristic have a similar issue.
Okay.
So basically, there's a reason why the real question is about characteristic 0. But I mean, except of course, if for the non-commutative geometry, this is an actual honest question, and you really do want to know this over Z, and the fact that it doesn't work over Z is disturbing.
Yeah.
But also, but for characteristic 0, it's more a question of the fact that it doesn't work in finite characteristic constrains you because it tells you certain types of arguments can't possibly work. You need some way of getting a necessary condition that uses the fact that your characteristic is 0. Now, yes. What works for the Pain-Levé case, and at least gives a necessary condition in general, is a general fact, which is that if I hand you a torsion point on a higher genus Jacobian, or an elliptic curve or a higher genus Jacobian, a non-zero torsion point, then if you degenerate the Jacobian and you're still in characteristic 0, that torsion point will remain non-zero on the degenerate fiber. And this also works if you take a degenerate Jacobian, I mean a generalized Jacobian, so it might be like semi-abelian or something, but it's basically you can never become trivial by degeneration.
Right.
Right. But that fails if you're going from characteristic 0 to characteristic P, if you have a P torsion point. And it also fails within characteristic P if you're going from an ordinary thing to something which is not ordinary. You can have your P torsion point become trivial again there. So those are that's basically, and so that at least is explaining something about what's happening in the Pain-Levé case. So in particular, so what's happening in Pain-Levé is that the A8 lattice is index 3 in the E8 lattice. And what that tells you is that if you look at a general fiber of your elliptic surface, on that general fiber, you actually have a canonical 3 torsion point on that fiber, which is basically the generator of the E8 lattice, of E8 mod A8. Yeah. So you get this canonical 3 torsion point, and that's the thing which is would have to be 0 to degenerate the E8. And so that's why you get those cases. And so similarly, one of the A7 cases can't degenerate the E8 because that quotient of lattices has torsion as well.
Yeah.
So that condition is enough to explain all the cases where I know things don't work.
Yeah.
But as I said, I'm not even sure how to compute that in higher genus to sort of figure out all the possible ways you might have some higher genus Jacobian with a torsion point on it. So I'm not sure how to even do that computably, let alone, show that it's actually a sufficient condition if it is. So that's a big thing. And certainly you can approach it as a geometric problem, certainly. It's also possible to approach it as a more familiar type of problem, because it does reduce to questions like, if I hand you a Q difference equation and a differential, if I hand you a type of Q difference equation, just what are the singularities of this Q difference equation? Can you degenerate it to a particular type of differential equation? Now, this is not necessarily easy because it includes cases like, can you degenerate Q area into area?
Yeah.
But it is possible that might be a way, at least give you another way of approaching this question there. Yeah, so I know the answer within Q difference equations.
Okay. Well, that's
but
good.
Going from Q to lower or within lower is harder. Right. But within lower, there's always a differential lax pair available, so you can try to do the differential analysis. And then
what about from the elliptic difference?
Well, that's easy because elliptic difference degenerates to everything.
True, but there are some.
Figuring out the specific limits are going to be hard, but yeah.
But there are these sort of multiply laced subcases which arise from it too. So you can go from E8 to F4, for example.
Right. So what that's doing is that's basically imposing some extra symmetries. And so one thing that this theory doesn't directly tell you about, but still can give you some insight into, is basically what happens when either you have some extra symmetry. Well, I mean, basically in general, you have some extra symmetry, which could take the form of for instance, you have a differential equation, except that your matrix is in a smaller Lie algebra, like the orthogonal group or what have you. And so you can still get insight from that, because you can still sort of say, well, it's still inside GL, and maybe there's enough information. So in particular, the fact that we can say a lot about the two-dimensional case, and the two-dimensional case, and GL and SL are very closely related, and SL and SP are very closely related, means that sometimes you always have some extra symmetry, and you can hope that that extra symmetry, when you sort of trace it through the Fourier transforms you're doing, may actually explain this. And in particular, I've done that. There's an 08 case that I've seen. There's a lattice pair for Penlevet's, for one of the Penlevet equations coming with an 08 structure, which can be explained in this way. For instance, it's coming from the usual second order lattice pair, retaining the extra symmetry. But in general, this is not going to be easy. And so the F4 case, I forget what the actual symmetry is. But of course, if you can specify what the symmetry is in terms of the surface, then you can again sort of figure out the hierarchy. Because so I believe what the F4 case is basically saying is, there's some involution on the surface.
Right.
And so moreover, it basically, and so you figure out what that involution is doing in this basis of pick. And then you can do a similar sort of decomposition where you require that that involution be allowed to act. And what that boils down to is any -2 curve that gets, any root of the root system that gets negated by that involution cannot be effective.
Right.
And so that gives you the extra conditions that have to be satisfied and would give you this F4 hierarchy. Okay. I believe that's my vague recollection, although it's been several years since I looked at the F4 case, but that's my vague recollection.
Thank you.
Yeah. So yeah, so I think in the elliptic version of that, there's a 2 torsion point, and you basically your 8 singularities are pairwise related by this 2 torsion point.
That's right. Yes. Yes.
Yeah.
Okay.
Oh, and of course, whenever you do that, you also have fewer isomonotony transformations, because they need to respect that extra structure.
Yeah, I have to try and understand that better. I'm not sure I understand it yet.
Yeah. But again, if the extra symmetry is coming from an involution on your surface, then what needs to be, then the condition is basically that the divisor class you're twisting by, the line monitor you're twisting by to get the isomonotony transformation has to be invariant under that involution. So it's not too complicated. I guess you get a little bit of extra things because you can also, you have this 2 torsion point, you could translate by, you could do a twist that sort of moves one of them by twice the 2 torsion point and then swaps them or something, which gets a little funny. Yeah, and the reason why I don't have, why the theory doesn't really tell you about other structure groups is because there's this Fourier transform in the picture, which can change the order. And so in particular, if you start with something that has structure group E8, it's an equation of order 248, but you apply a Fourier transform, it's going to be some other order, which will have, in general, absolutely nothing whatsoever to do with representations of E8. And so it's not at all clear how to fit that into this geometric picture, because it really then is not going to be something intrinsic to the sheaf. It's going to be something that really involves the ruling in some very non-trivial way. This is a theorem. Although for quite a while it was just a conjecture, but so the first thing to note is that there are sort of 2 different ways of predicting the number of continuous deformations. One is just this parameter counting. The other is, if you look at your local singularities, each one of these irreducible things has at most, if it's a difference equation, it basically has at most 1 continuous deformation. There's only 1 parameter that has the freedom to move continuously. Oh, sorry. I take that back. There's only 1 parameter that has the freedom to move discretely. All of the other parameters move continuously. And so that gives you another way of counting where you basically say, what are the local continuous isomonotony deformations and count that up. So the first thing is that you can show that that gives you the same number. The other thing, but the reason why this is tricky is that the continuous isomonotony deformations only really exist at in the non-autonomous level. Or rather, if you go autonomous, you have this symplectic structure. So you have, if it's 2D dimensional, you have 2G different directions you can deform in continuously, just by taking different Hamiltonians. And so, there's no, and it's not clear how to tell which of those directions come from continuous isomonographs deformations. That's still an open sort of question of how to figure out sort of which slice of that comes from the actual continuous isomography problems. So that's a bit of an issue. However, so it really is an entirely non-commutative thing. But in non-commutative land, what you can basically, you can split the continuous deformations up into their sort of local pieces, which you can show actually agree with this local picture of just deforming your local equation. And then there's the piece where you deform the actual curve you start with, which in that sort of scenario is going to be, is some base curve which may have some fiber sticking out for each singular point. So for instance, in the differential case, if you have 5 singular points, you're going to have a double curve with 5 fibers sticking out, possibly with multiplicities. And then, so you get deformations coming from there. But you can show basically in each of those cases that those deformations really do survive to give you infinitesimal, I mean, if you deform your surface along in that direction, there's a corresponding deformation of your sheaf to sort of extend it to that nearby surface. I mean, basically part of the tricky problem is turning it into an algebraic question. So you have to, so it turns into a deformation theory question of basically, does the sheaf deform as to a nearby surface? So part of the question is sort of figuring out what the nearby surfaces you need to look at are. But okay, so that works. Now, the thing that's annoying there is it turns out that this number you get of continuous deformations is invariant under the Fourier transform. It's actually intrinsic to the sheaf, which in terms of deformation theory, it has to be intrinsic, because you're just asking, for which nearby surfaces can you deform the sheaf? So it's just some abstraction question. But none of these ways of calculating it, sort of that naturally tell you what the deformations ought to be, actually are invariant into the Fourier transform, are obviously invariant to the Fourier transform. Because it's only basically because there's a way of translating it into something where it's some sort of Euler characteristic that lets you actually turn it into, I mean, there's a way of computing it which is intrinsic to the sheaf, but it's not easy to prove that that's actually agrees with any of these other directions. You basically have to do an inductive calculation of, following it as you blow up. So there's still a question of sort of how to describe the continuous deformations in a better global way. And similarly, there's sort of this, if you look at what's happening in the Painlevé cases, you have Painlevé 4, where your continuous deformation is moving the 4th singular point. But when you degenerate Painlevé, you're no longer moving the singular points, you're degenerating within one of your singular points. And so you're changing the type of deformation you're doing when you hit that limit. And so again, it's a little tricky to sort of track that, yes, each continuous deformation at one level survives in some sense as a continuous deformation on lower levels. But another thing I don't understand. So from Sakai's paper, we know that for Painlevé, and then presumably for any other case, for Painlevé, the continuous isomonographs deformations are limits of discrete isomonographs deformations, or at least the continuous Painlevé equations are limits of discrete Painlevé equations, which tells us that these continuous deformations should be limits of twisting by line models. This is a very unnatural thing to be talking about in geometry. So I have no idea how to make sense of that. So this is, there's a number of questions that are not necessarily at the level of holes in proofs, but are definitely holes in understanding. And the continuous deformations are still where a lot of those are. But it is easy enough In each of these cases, the code I have that tells you, there's 61 Pan-Lavey-Lax pairs also tells you which ones of them have continuous isomorphism deformations. So algorithmically, it's easy to do with. It's just, conceptual ideas that are still missing a little bit. And of course, for the four-dimensional cases, sometimes you have two continuous isomorphism deformations. Well, it's weird because for genus 3 or higher matrix Pan-Lavey, it's 61 types again. So there's just one thing you can do, but only in genus 2, that sort of slightly splits it up a little bit. It's basically you have these two singular points that are getting split up at the end, because you have, it looks like you just basically multiplied all the it looks like these Lax pairs for Pan-Lavey would just multiply everything by 2, except that the last singularity gets split into 2 pieces. And if those two except points you blew up at the end are not different, then you actually have an apparent singularity and you turn into a Pan-Lavey case. Or basically it's like 2 copies of it, of two independent Pan-Lavey-Lax pairs that are direct summed. So it splits up into something reducible. However, if that point is sufficiently singular, you can actually, there's one case, I think, where that point can actually be the same. Those 2 points can be the same. But that breaks once you're in the higher case because the multiplicities are now different. And so you can no longer sort of, that -2 curve you would have is no longer a disjoint from your curve. So it's something weird that only shows up in Pan-Lavey and made in the genus 2 case, and I'm not sure. And I think it is actually, it may in fact only be Q difference. But yeah, my recollection is that it's only in the Q difference. It's only one Q difference case. It's kind of weird. And I'd have to. I'm not sure if I've written that down anywhere, but I'd have to Well, you already know that. It's the same number as in your paper. Well, so I think actually in the Garnier case, I'm pretty sure one can actually do that, without having to resort to computers. I think it looks like it's possible by sort of using a different approach that's no longer inductive. But I think it's possible to actually figure out what the different possibilities are purely conceptually. So at the very least, for each of the 5 cases other than differential, it looks like there's an explicit polynomial formula formula for the number, which is polynomial in M. And for the differential case, it looks like there's an explicit description in terms of some kind of colored partitions. So it looks like basically one should be able to do the classification completely explicitly for all M. And so then it's just a question of sort of figuring out, how to describe that and how to count which ones have how many continuous deformations which ones have from whatever description you get. So I think the Garnier case should be doable, and the matrix Pan-Lavey case should also be doable because it's basically the same classification as Pan-Lavey. Yeah, no, I think the extra weird Pan-Lavey case is, it's something like A8 with some, it's like a degeneration somehow of A8, so it's not really all that interesting because it's not really an isomorphism problem. But because the deformations you're doing there, it's just an order 3 thing, so it's not really an interesting equation. But I think it has to be something that degenerate, because as I said, it's only like one case.